Okay, let's dive right into this explainer. Today, we're going to tackle those high-yield, tricky exam questions surrounding Layer 2 of the OSI model, the data link layer. Look, whether you're prepping for your CCNA, grinding through a cybersecurity degree, or you're gearing up to be a systems administrator, grasping how local networks actually talk to each other is, well, it's completely non-negotiable. We're going to take that dry textbook theory and translate it into practical, memorable knowledge that'll stick in your brain for good.
Here is our study roadmap. We'll quickly cover the basics of the data link layer, pit MAC addresses against IP addresses, figure out how switches actually route frames, look at error control, dive into VLANs, and finish up with a real-world troubleshooting scenario. Let's get to it.
Starting with Section 1, Meet the Data Link Layer, let's lay down those foundational mechanics.
So if you're taking any networking exam, your professor will almost certainly ask you to define its primary job right out of the gate. It sits right there between the physical layer, which is all those raw electrical bits and cables, and the network layer, which handles the big global IP routing. But what is Layer 2 actually doing in the middle there?
Well, the absolute crucial takeaway is that while other layers are out there handling global internet routing, Layer 2 strictly rules the local network territory. It takes those raw ones and zeros from the physical cables or the Wi-Fi signals and packages them into these neat, meaningful units of data called frames. This is literally what allows devices on the very same physical network, like your laptop and your smart TVs sitting on the same router, to talk to each other securely and reliably.
Moving to Section 2, MAC addresses versus IPs. Let's untangle this one.
This is easily the most common exam trap students fall into. People throw IP address and MAC address around interchangeably all the time, but mixing them up on a test will absolutely tank your score. Your IP address is logical. It changes based on the network you're connected to, kind of like when you move from your home Wi-Fi over to a local coffee shop. But your MAC address, which stands for Media Access Control, is a physical, 48-bit hexadecimal identifier that is literally burned into your network card at the factory. It basically never changes.
If you're ever sitting in an exam completely blanking out, just anchor your memory to this apartment analogy. When data is traveling across the world, the routers use the IP address to find the right apartment building. That's the correct local network. But once that data actually arrives inside the building, the local switch uses the MAC address to find the exact door, the specific device that the data is meant for.
And to move these MAC addresses around, Layer 2 encapsulates data into a structure called a frame. It's essentially a digital envelope broken into 3 parts. First, the header, which contains the source and destination MAC addresses. Then the data section, which is the actual payload from the upper layers, maybe a chunk of a YouTube video you're streaming. And finally, the trailer, also known as the frame check sequence, which is tacked on to the very end to ensure the whole shebang wasn't corrupted while traveling across the wire.
All right, Section 3, how switches route frames. Let's talk about the hardware.
The switch is the absolute workhorse of Layer 2. And this right here is a classic certification question testing your understanding of how it actually thinks. A switch operates by building a MAC address table. It essentially memorizes which computer is plugged into which of its physical ports. But what happens that very first time a new device joins the network and the switch hasn't learned its address yet?
It does something called unknown unicast flooding. Because the switch desperately wants to guarantee this unicast data reaches its destination, it basically shouts the frame down every single hallway as a broadcast, asking, "Hey, is this your MAC address?" The device that actually owns that MAC address will reply, and the switch goes, "Ah, there you are," and records its location in its table for next time. It's an ingenious little mechanism.
And that exact learning behavior is the foundation of why modern switches are such a massive upgrade over older networking hardware. Think about the contrast here. A hub operates down at Layer 1. It's a completely dumb device. It doesn't understand MAC addresses at all, so it just blindly yells data out of every single port, all the time, creating a ton of network congestion. Switches, on the other hand, are Layer 2 smart devices. By actively using those MAC tables, they send data only where it needs to go, which makes local networks incredibly fast and efficient.
Which brings us to Section 4, error control and collisions. Let's look at what happens when traffic goes wrong.
Because in networking, devices are basically constantly trying to talk over each other. For wired Ethernet, this step-by-step mechanism is our bread and butter. It's called CSMA/CD, or Carrier Sense Multiple Access with Collision Detection. It's really just a very polite conversation protocol. Before a network card sends a frame, it literally listens to the copper wire. If it's quiet, it sends the data.
But if two computers happen to send at the same exact millisecond, their electrical signals physically smash into each other. The network cards detect this collision, immediately stop, wait a random fraction of a second, and then try again.
Now, what is super fascinating here is how the physical medium totally changes the rules of the game. Wired Ethernet uses collision detection because, well, you can easily measure voltage spikes on a copper wire. But Wi-Fi, operating under the 802.11 standard, uses CSMA/CA, collision avoidance. When you're dealing with invisible radio waves midair, it's nearly impossible to detect if they're crashing into each other. So Wi-Fi devices essentially ask for permission to speak beforehand so they can avoid collisions entirely. It's a real game changer.
Oh, and remember that trailer we mentioned at the end of the frame earlier? It holds the cyclic redundancy check, or CRC. The sending computer runs a complex math equation on the data and drops the answer right in that trailer. When the frame arrives, the receiver runs the exact same equation. If the math doesn't match up, maybe a bit flipped due to some random electrical interference, the receiver just instantly drops the corrupted frame, and the upper layers have to request it all over again.
Let's move on to Section 5, Advanced Concepts and VLANs. We're leveling up to enterprise territory now.
These are the concepts network engineers use in corporate environments every single day. A virtual LAN, or VLAN, allows you to logically slice up a single physical switch into multiple, totally isolated networks. Imagine a physical 24-port switch. Normally, everyone plugged in gets flooded with everyone else's broadcast traffic. But by assigning specific ports to different VLANs, you can keep the accounting department completely invisible to the IT department, even if they are plugged into the exact same physical box. It provides a massive boost for both security and overall network performance. And to make VLANs actually work in the real world, you absolutely must know the difference between an access port and a trunk port. You plug your laptops, printers, and regular end devices into access ports, which belong to just one single VLAN. But let's say you have multiple switches spread across a huge office building. You need a way to pass all those different VLANs between the floors, right? That is exactly what a trunk port does. It acts as a superhighway, carrying traffic from multiple VLANs simultaneously by tagging the frames, so the receiving switch knows exactly who belongs where.
Okay, question time again. What happens if someone accidentally plugs a cable into two ports on the same switch, creating a loop? Now, I know it sounds like a ridiculously silly mistake, but trust me, in a messy server room with hundreds of tangled cables, it happens. And without safeguards, this simple human error is catastrophic.
Without a safeguard, you get a broadcast storm. See, Layer 2 frames don't have a built-in time-to-live expiration timer like Layer 3 packets do. So a looped frame will just circulate through that switch infinitely, multiplying and eating up 100% of the bandwidth until the whole network essentially melts down. Thankfully, we have the Spanning Tree Protocol, or STP. It acts as the ultimate safety net, mathematically sniffing out these loops and temporarily disabling redundant ports, keeping the network safe while still allowing you to have physical backup cables plugged in. Which brings us to our last stop, Section 6, a final troubleshooting exam scenario. Let's put this into practice. Knowing definitions is great, but applying them is what actually gets you hired. When a user complains that the internet is down, true professionals don't just guess. They troubleshoot by walking up the OSI model step by step. You don't start at the top checking the DNS server, no. You start at Layer 1. Is the cable physically cut or unplugged? Then you move to Layer 2. Is the switch actually learning the MAC address? Then Layer 3 for IP issues, and so on. It's a highly structured process of elimination.
And that brings up a really crucial point. If a physical cable is unplugged, Layer 1 fails immediately. But what does that mean for the data link layer above it? Well, actually, scratch that, it means Layer 2 completely crashes as well. Because without the physical transmission of those raw bits, there are no frames, there's no MAC addressing, and there is no local network. I'm going to leave you with that thought to ponder, because truly understanding how failures cascade upward through these layers is the mark of a networking expert. So review these concepts, lock in these mechanisms, and you are going to absolutely crush your exams. Thanks for sticking with me, and keep studying.